Hello, this is our monthly recurring meeting of building electrification. We're going to have a guest speaker today who's going to talk about solar, but a quick promo right now. I'd like to uh, let you know we have a large group of volunteers who are part of our program, and they're calling ourselves the New Jersey Electrification Coaching Network. And each of us has been trained in the steps to electrify a home, and we each are available to help you electrify your own home. And I'll put a link in the chat so that you can actually sign up for a coach if you're interested in this. With that, I'd like to introduce Mike Winka. He's our guest speaker today. He's a professor, a consultant, retired lead engineer scientist for the New Jersey BPU. He has a vast knowledge of clean energy programs currently implemented by the BPU and also being implemented by the New Jersey New Jersey utilities under control of the BPU. He currently teaches solar to Princeton Adult Education and is going to show to us his tried and proven slides on solar. So thank you, Mike. I appreciate you offering to do this, and it's
Great.
now up to you.
Thanks, Steve. Great. So I'm going to go over what I call for the Solar 101, sort of the basics, give you more of the detail, just so that how you can put a power plant on your roof. And my best advice in all of these presentations is to hire a reliable solar professional. I'll talk about where you can go look for data at the end of the presentation. There are websites out there that evaluate and rank solar installers or give you advice on solar installers. My goal in all of this is to arm you with good information so you can decide what's the most cost-effective system that you can install. Just to give you the information on the details. So when a contractor comes in and says something about, here's the amount of solar we can put on your roof and here's how much it's going to cost, you can run through that and do your own analysis. But I can't design the system for you. So all of the calculations that we run through are basically estimates. They're good examples, but if you're going to go out and buy solar, you're going to need to think about more things than just doing a simple payback analysis is what I run through in these slides. So before we get into the Solar 101 details, I just want to talk about, electrifying everything and the sort of strategy of moving towards electrifying the building and transportation sectors. So you can heat, light, cool, do your own transportation, charge your EVs, powered with your own fuel, and what that takes to be able to do that by 2030, 2035. We have to start thinking about these strategies together in an integrated, more holistic fashion, as opposed to the way they're set up right now in little different silos. And solar's over here with EVs, and batteries over here, and energy efficiency and heat pumps over here. It's really got to be thought about more like a 3D chess process to build those policies and strategies to electrify the building and transportation sector. So just a plug for how we have to start thinking about all of these things together. So typically when I run through this presentation, I will make the analogy that it's similar to, I'm going to teach you math. I'm going to show you why 1 + 1 is 2, what's the distributive property and associative property of math, of addition and subtraction, and then I'm going to give you the calculator after you learn all of those properties. But I'm going to flip that on its head here. I'm going to give you the calculators up front. I'm going to show you what they do. And then I'm going to fill in the details of what those properties are in those calculators that allow you to calculate, how much solar you can put on your roof. So this is a slide of a number of the sort of calculators that are out there. The easiest one is Google Project Sunroof. You stick in your address and within a minute it comes up and gives you a pretty good estimate. The next one, PV Watts, is basically a calculator that was developed by the US Department of Energy the National Renewable Energy Lab probably 25 years ago, and sort of is the basis for a lot of the um, calculators that are out there. And you see Energy Sage, Solar.com, SunPower. There's various ones out there, and they all ask you for different information. They're all relatively the same, and they help you to decide how much solar you can put on your roof. So this first one is Google Project Sunroof. You put in your address. That's my house over here. I put in that address. It tells me how much space I have. Here's direction is north. This is south facing over here. You see, I don't have much south facing roof. I have east and west. I have areas that are shaded. It will give me an estimate of about 8.5 kW of solar that I can put on the roof in different locations. And I'll talk about that and how much energy that can produce over the year and how much net savings I have if I plug in my utility and my utility bill information. You can also do it for the township. And since I do this presentation for the Princeton Adult School, this is Princeton Township. Here's Princeton Borough, which they're all one and the same now. And I'll actually calculate the entire area of Princeton, what roof space is available for solar and how much solar they can put in. And you can run through that calculation. So about 80% of solar of Princeton's annual electric use can be provided by solar with the solar within the roof space in Princeton. Again, that's averaged over the year. And as we talk about in this presentation, the sun rises and sets. So your solar power starts off as 0 through the day and also varies over the year. So while it can produce 80% of the annual use, you have to think about it. Can it produce it at 9 o'clock at night? And what does that mean? Can I produce it at 9 o'clock at night in the winter time? So the next one is PV watts, and that's sort of the basis for a lot of the calculators that are out there. I'm going to stop sharing this screen here, and then I'm going to bring up the PV watts calculator. So can you see that? All right, so that's the PV watt calculator. You just plug in PV watts in Google search and it'll come up. You put in your address right here to get started. So that's my address. I click that along and it'll come up with a Google map of the location. You can zoom in on this, hit go to system information, and typically it'll come up. I don't know why this did that, but typically it comes up as a default 4 kW system with all of these things set here, tilt, angle 20%, azimuth 180 degrees. It'll say what sort of modulars. You can play with all of these. And we'll go through in this presentation what some of these things mean and why you can plug them in and what they mean. What is the tilt angle? What's the azimuth? Why do you want to put in premium, thin film, or standard panels, modulars? What's the system loss? So all of those things can be played with. And again, I'll talk about all of those things as the properties in this calculator, and then we'll come back and run through the calculator again. But you can ask it to go calculate the results. And for that 4 kW system, which is the default number in the calculator, it'll tell you how much solar radiation in kilowatt hours per meter square per day you're going to receive based on your location, and how much that 4 kW system in terms of energy will produce on a monthly basis, and the total amount of electricity that's generated on a monthly basis. One of the other things that you can do with this, when you go, you can click on here and it'll come up with a Google map of your house. You can plug in a digitized system on your roof just by clicking the dots, asking it to save, and it'll tell you that's a 3.2 kW system. I go calculate that, and that 3.2 kW system will generate 4,209 kilowatt hours per year. This is the amount of energy it'll produce on a monthly basis. You can even look at it if you want in more detail on an hourly basis. But monthly is what you get your electric bill to, excuse me, as you want to calculate that against your electric bill. So again, you can play with this. Cancel that. We can make it bigger. We can show it over the entire roof. Of course, there's different directions and different slopes on the roof. So those will calculate out differently, but that's a larger system. It's not all going to be the same tilt. It's not all going to be the same azimuth. I'll talk about what those mean. And based on that system, you can see how much energy that produces. That 12.5 kW system produces more energy. And we'll talk about that further in the presentation. So I'm going to stop here and go back to the presentation. So again, this is what I showed you in that opening slide for PV watts. Next. I did that, but so that slide about the site information. And just giving you information on all of these factors that we're going to talk about in this presentation and how you can play with them and how you can calculate the size of the system on your roof. So here's that 7 kW system I talked about. The old PV watts actually calculated the amount of avoided cost on a monthly basis, but you can do that yourself. You can plug in your current retail rate and do this calculation and see on a monthly basis how much that would mean in terms of avoided cost on your bill. Excuse me. Yeah. Okay, so this presentation is basically for a single family home that has a roof space that's not fully shaded by trees or another building and is not an historic designated home. There's different rules for that historic home. It's for installation on a roof. You may be able to put a ground mounted system, but again, that might trigger some additional local zoning authority. If you live in a condo, you have to check with your condo board. There is requirements in the statute that allow you to put solar in a condo development, but you have to check with the condo board. And if you live in a multifamily home that you don't have access to your roof, you can explore something called community solar, where you can buy the solar electricity offsite, similar to the way you would put it on your roof. Some of the things that we need to talk about is some of the basis for solar sizing your solar system. You have to know what your rate is, and there's two types of electric rates. There's residential and non-residential, and this presentation is for a residential customer. A residential customer typically pays one fixed price. It pays a demand charge and an energy charge in the bill. So you're getting the entire avoided cost of your retail rate. Solar only goes against the energy cost in your bill. Since as a retail customer, you have one fixed rate, it goes against the entire retail cost. But a commercial customer or an industrial customer pays two rates. They pay an energy charge, $1 per kilowatt hour, and they pay a demand charge. And that's to separate out the demand that some larger energy users have. You can think about that as you're a restaurant owner. You're buying bread from a bakery. You don't have the ability to store the bread. You have to use it right away. The bakery is only open from 8 in the morning until 3 o'clock in the afternoon. But your key customers come in at 9 o'clock at night on the weekends. So you have to pay the bakery to stay open on the weekends at 9 o'clock at night. That's the demand charge that you basically pay as a commercial customer. The important point is the solar net metering only applies to the energy side of that rate, the dollars per kilowatt hour, not the dollars per kW, which we can talk about in the next presentation. Battery storage actually goes to help against the demand charge. So some basic terms that we want to talk about in this presentation is you want to know about the kilowatt hours. So kilowatt hours is the amount of energy that you're using. We just talked about that demand charge. Kilowatts is the amount of power. Power is equal to energy divided by time. So it's kilowatt hours, not kilowatts per hour, excuse me. So you have kilowatt hours divided by hours. Only in the English unit system would you have a formula like that. In the standard units, it's joules or joules per second, which makes a whole lot of sense. But in the English units, it's kilowatt hours and kilowatts. You have to think about kilowatts in terms of install capacity. And we also talk about kilowatts in terms of capacity factors. That capacity factor is how long is the sun shining to generate electricity, and that capacity is how much you can install of the solar panels on your roof to make energy for you to use in your home. A couple of terms you'll hear, watts. 1,000 watts is 1 kilowatt. 1,000 kilowatts is 1 megawatt. And if just to put it in context, if you use 100 old 100-watt light bulbs for 1 hour, that's a kilowatt hour of electricity that you're using. The 100 watts is capacity. So you use 1 kilowatt hour of electricity, cost you about 19 cents per kilowatt hour. Just in terms of thinking about energy efficiency, 14-watt LED light bulb used for 7.5 hours is equal to 1 kilowatt hour, cost you 19 cents. Or another way to think about it, I can leave that 14-watt light bulb on for, I can have 71 14-watt light bulbs on for 1 hour, and that's 1 kilowatt hour. So just to think about energy efficiency in those terms. Just to have some background in terms of, how much solar we've already installed in New Jersey. It's just a little over 200,000 installations since we started the program in New Jersey in 2000. You can see 2000 there was 6 installations. In 2001 there were 2. We now have routinely several tens of thousands of systems installed on an annual basis in New Jersey. While 200,000 installations is great, that's just about 10% of the buildings in New Jersey. And that 5% of the buildings in New Jersey is about 7% of the annual electricity use, about 5,000 megawatt hours. So you can see in 2001, installing about 23 kilowatt hours. Now we're installing about 400 megawatts per year. So a significant jump in the number of installations of solar over the year. It's generating about 7% of the annual electricity needs. Back in 2000, at 9-10 kW of solar installed on an annual basis. In New Jersey, on an annual basis, we install that amount of solar every 15 minutes. So a significant increase in the number of installations. So first things first, I said, if you want to put a ground-mounted system in, you're probably going to need to go to the zoning board. You probably don't need zoning board approval if you're going to put it on your roof, given that there's 200,000 installations. Every municipality has seen several hundred installations already, 500-600 installations in every municipality across New Jersey. So it's not a zoning board approval if you're going to typically install it on your roof. You will need building code approval. Again, if you're in a historic site, it's a different approval process that you have to go through. You need to get approval to interconnect to the utility system. The utility owns the system. You have to interconnect to send your electrons out into the system for you to store your electrons on the system. You also need BPU approval for the incentive. It's called an SREC 2 now, Solar Renewable Energy Certificate. And I'll talk about what an SREC is later on in the presentation. So you can reach out to your zoning code official. They're pretty helpful. They'll tell you what the process is if you're thinking about doing this on your own. Typically, this is all done with the contractor. You can reach out to BPU or your utility to get information about the interconnection. I put PSE&G here because I do this presentation for Princeton. But you can go to the BPU website, the Clean Energy website. You can see every website for all of the utilities throughout New Jersey. And you can reach out to BPU to talk about registering for these incentives that help to pay for the solar system over time. And I will talk about what that is. So a couple of things. First things first is you probably want to think about energy efficiency. The more energy efficiency you can do before you buy a solar system, the smaller the system you can put on your roof and the shorter the payback period that you have. There's also a flip side to that. You can do energy efficiency after you install the solar on your roof. But again, that solar capacity, the interconnection to the utility system is limited to your historic usage per what's called the net metering tariff. So you have a tariff that allows you to interconnect, that gets you to be able to sell your electricity into the grid and to then use your electricity that you stored on the grid when the solar system is not generating electricity. So that net, and again, you can only net meter up to your usage, your historic usage. So if you're thinking about putting a large 100 kW system on your roof, and you don't have that amount of electricity that you use, the electric utility company is not going to approve it. It's only going to approve your historic usage under the net metering tariff. You set your net metering usage back to 0 annually, so you don't accumulate all of that. If you have excess electricity that you've generated, you get paid at the wholesale rate, which is about 2 cents a kilowatt hour. Again, one of the things why you don't want to think about this as becoming a real generator where you're going to sell power at 2 cents a kilowatt hour. The payback period is significantly long as opposed to the payback period for your historic usage at the retail rate, about 19, 20 cents a kilowatt hour. Any underage that you have used that your system isn't generating, you have to pay, and you get to set that date once based on the maximum performance of your system. So a couple of other things. First things first is the age of your roof. You're putting these solar panels typically on your roof. Does the roof need to be replaced? How old is the roof? Can it support the solar panel? So typically the roof can. I mean, each solar panel is about 30 to 50 pounds per panel. It's going to put a force on your roof about 2 to 3 pounds per foot squared, which is relatively small. Most roofs can handle that, but again, part of the contractor's responsibility is to look at the roof and see whether it can support the solar panels. There is a structural issue. You may want to think about insulating the roof to reduce heat gains and heat losses. And how's it going to affect if you did replace the roof within the last couple of years? What's the warranty on the roof? You want to call the roofing contractor to understand putting solar on your roof. How does it impact your warranty on your roof? Do you need insurance? You want to call your insurance company. And there are tax issues about the incentives that you get. You want to call your tax accountant to do that. Solar PV is exempt from property tax increase. So most things that you improve your property go into increasing the value of your house. Solar will increase the value, but it doesn't increase the property tax on your house. Solar also is exempt from sales tax in New Jersey. You're going to need a warranty to get the incentive. You have to have a warranty. We'll talk about that. It has to be a full, not limited 5-year warranty on any manufactured components. So that's one of the requirements to get the incentive in New Jersey. You have to install this with a licensed electrician. So that's also one of the requirements, and has to be installed with a licensed home improvement contractor. You can go to the New Jersey Department of Office of Consumer Affairs to look up the requirements for licensed electricians and contractors. In other states, they have to be installed with a certified solar contractor who is certified by the North American Board of Certified Energy Practitioners, NASAP. We don't have that in New Jersey. Basically, we built the system somewhat before the certification process. So you just need a licensed electrician and a home improvement contractor to install your system. And the reason you need a licensed electrician, the building permit requires what's called a single line diagram. You can see the example here. This is just an example of what a contractor is going to submit to the municipality for your building permit. You see the details of the solar panel on the left-hand side and the single line diagram of what your panels will do so that you can get approval from the local system. You need that approval. You need that approval before you can get approval from the utilities to interconnect. You have to have the approval of your system to be able to be energized to send your power out into the grid. You also may want to think about your electric panel. If it looks like something on the left-hand side, you want to upgrade that panel from 100 amps to 200 or 400 amps, depending on what you also want to do as you want to think about this process of not only installing heat pumps and solar and batteries and other heat pump like equipment for dryers and induction stoves. So you want to think about how that is all going to fit into your plan overall. The cost for upgrading the panels runs a couple of $1,000s, depending on site conditions. If you have underground service, it can cost upwards of over $10,000. There is currently a federal investment tax credit, and the utilities have something called a make-ready incentive. So they'll pay for the wire that goes up to your house. And now with the new heat pump incentives that the BPU just approved for the utilities, there's incentives for panels and wiring in the heat pump side. There's also incentives, as I said, make-ready incentives on the EV side. You can't pile on those panel incentives. You have to work with them in conjunction. So let's talk about the interconnection process. It's basically a two-step process to interconnect. You put together your designs, you submit a preliminary approval to the utilities. They will approve that based on the size of the system. Sometimes based on conditions that are out in the field, the system may need to be a little smaller, a little bigger. You get that final approval to energize your system. And as I said, one of the things they look for is that the local authority approve the system on your roof before you can energize. So you can't get the solar incentive until the utility approves your system to energize, to connect to the utility system, and you can't get that until you have local building authority approval. There's different levels of interconnection approval. Basically, at the residential level, it's pretty straightforward. As I understand it, there's no fee. That might be changing in the future. It's called a level 1 inverter for things that are less than 10 kW. Typically, on a residential system, you're going to put less than 10 kW kilowatts on your roof. Typically, the average size in New Jersey is about 7 kW. But if you're larger or you run into some issue, there's a level 2, level 3 interconnection approval process. You also need to look at what's called a suitability map or a hosting capacity map. Can you install solar in the location that you're at? And that is called the hosting capacity map. Before I go into that, let me talk about, in general, how net metering works. So you put solar on your roof. It gets energized from the solar radiation from the sun. That is creates DC power from the panels. They go into an inverter. That inverter changes it to AC power to be used in your home. If you're making more electricity than you're using, it goes out through the meter. The meter sends it out to the grid, which basically is storing your electrons for you. It's not exactly storing. The electrons get used right away, but the meter is flowing backwards as you send your power out to the grid. When the sun isn't shining and you're pulling power off the grid, the meter is running forward. That's why it's called a bidirectional meter. It runs forward when you're pulling power off the grid. It runs backwards when you're sending your power back onto the grid. And this suitability map or hosting capacity map tells you whether you can install solar on the feeder locations at the local level. So you can see here on the left-hand side, this is a map of Princeton. Whoops. Previous. Use a touch screen, so it's a little touchy. So every one of these dots is a transformer, a pole-mounted transformer. It's one of those drums you see on the top of a pole. Typically, a pole-mounted transformer will have 3, maybe 4 homes connected to it, depending on whether there's a business. There may be more or less transformers. You can see what looks like a feeder here, all of these yellow. We'll see on the map on the right-hand side a little difference in terms of the feeder. The green level says you can install any size system in that. Yellow means there's some limitations to being installing that, but typically not at the residential level. Red means, and in this map there's no red, but you can't install more than 100 kW. Doesn't affect a residential level, but maybe at a commercial level, you may be limited in the size that you can put if you're in the red zone. You can see that here on the right-hand side. Excuse me. Several of the feeders are red, which limits the amount of solar that you can put on those feeders to something less than 100 kW. You can see the sort of design here that we talk about, a radial feeder. Typically, systems were built around a substation that radiated out from the hub of the substation. Basically, that was the design of electric power systems, mostly radial systems. You can see the spoke and hub design here. So this black area is you can't add any solar in those locations. The factor of safety of adding solar onto those wires and those transformers has been exceeded or met. And again, that's a safety issue with the system. And until that system is upgraded, you can't add any more solar. So no residential system can put a 10 kW system in these locations. Part of the discussion now is who's going to pay for the upgrade of that system. Should the people that have solar on all of these lines pay for the upgrade? Should society in general pay for that? So should the next person that wants to install solar in these locations pay for that couple of $1 million upgrades to those systems? So that's part of what we talk about when we talk about modernizing the grid. How do you improve the hosting capacity map for solar in some of these locations? But you can go to the maps and see, as you can see, most of it is doesn't have any limitations on it. Some of them are limited in terms of the size of the systems you can put on, but typically not in terms of limitations for residential systems. You can go to these different websites and see about the metering requirements. And there's 2 metering requirements in New Jersey. You have a production meter, and I'll talk about that, what that means in terms of calculating the incentive that you get for solar. There's a website here for all the information on net metering and interconnections, and information on all the utility suitability maps and hosting capacity maps that you can go to see if you can put solar in the location on that utility system. So let's talk about this in a little more detail, what it means to interconnect to the system, and net metering to the grid. So here is a line of panels. We call them a string of panels here. They're all connected to this little system here called a combiner box. It takes all those wires, combines them, unique definition, combiner box, and sends that back out to the inverter. So this is DC power here coming through the combiner box into the inverter. The inverter has a disconnect on the DC side. So if something happens, it disconnects from the system, and it also has a disconnect on the AC side. Those are required by code to be installed. And then the electricity from the solar goes through the panel and back out to the grid, or is being used inside the house. Here's that second meter that we talked about, that production meter. So the incentive in New Jersey is based on the amount of electricity that you're producing from the system. If you just relied on this meter, that meter, as we said, was a bidirectional meter. It spins backwards when you're sending electricity onto the grid, and it spins forwards when you're using electricity from the grid, in addition to your solar that you put onto the grid. That system is a net metered system, so it can net out to zero. It's not going to tell you how much energy you actually produced. So you need this second meter on the system to actually report and calculate how much electricity you have produced, so they can calculate the incentive for you on an annual basis. So let's talk about that in inverter for a second. So typically you're installing what's called a grid tie inverter. And when there's a power outage on the grid, the typical older inverters would disconnect, right? So we said there's this disconnect switches on the system. The inverter senses that the grid is out and disconnects you from the grid, so that you're not sending power out, and that there's not energizing of the system, of the utility system. So when they're working on it, there's not electricity going through the wires. That's a safety system on your, a safety device on your system. So typically it would go out. There's new smarter inverters that can ride through some minor transient conditions. So I showed you the grid down here. Typically, again, there was that hub condition that they built a substation here and they radiated out these wires. They're now connecting these wires so that if your system went out here, the electricity would find a separate path and get electricity to you instantaneous at the speed of light. You may have experienced the situation where your lights went out, or your TV or your computer went out and then came back right on. That's what's happening with what we call smart grid, and being able to reconnect these wires where they were typically radial systems, so that the system has more reliability, more resiliency in the system. But what happens with the grid-tied inverters, once they sense that grid is out, they will shut down, and you're not sending out power to the grid, or you're not storing your electrons on the grid. So you're losing those electrons. Now there's the smarter inverters that can ride through that little transient condition that will sense the electricity went out, shut down, and then test it back and go back up again if the electricity in that section of the wire is on. If it goes out again, and will trip out again. So they're called smarter inverters. But to get to the next level of inverters, as we're putting more and more inverter-based systems on the grid, we have to get really smart with the inverter. The inverters right now just send electricity that has the same voltage and the same frequency as the grid. We'll talk about how that has to change to very smart inverters, which are called grid-forming inverters. They send out electricity that helps to set the voltage and frequency of the grid, not just mimicking what the voltage and frequency are. So that whole grid has to change to be upgraded in the future as we add more and more solar and wind to the system and more batteries to the system, as opposed to the traditional power plants that are out there. So I'll show an example of that. On the left-hand side, each one of those examples is a power plant. They're burning a fuel to make steam, to send into a turbine, to spin a turbine to make electricity. And they're all connected to the grid. They're connected in what's called synchronous generators. So if you turn your lights on in this area, in this generator, that generator slows down because you're pulling power off that generator. All of these other generators are connected to the grid synchronously. Sense that this generator is slowing down, they speed up a little to keep that grid power at a certain voltage and frequency so that it always maintains that frequency. What happens as you're adding more and more inverter-based systems, they don't have that same synchronous. They're connected to the grid, but they don't have this quality of spinning generators. Even though wind is a spinning generator, it's an inverter-based system as opposed to a spinning generator, a synchronous generator. So the system has to change to allow that to occur with smarter grid-forming inverters. If we had all inverter-based systems, that would be fine. The system would be able to operate, but it's changing from some of the system having spinning generators to some of the system being inverter generators. As it transitions from all spinning generators to inverter-based, the grid has to account for that and be upgraded to account for that. How do you want to do that? Do you want to pay for grid-forming inverters? Do you want to pay for some clean generation to be out there, like small nuclear power plants or other renewables that you have to pay for to generate that electricity when the inverters are not operating? And the reason for this, we just take a little sidebar excursion from Solar 101. This is a little curve that's called the duck curve. You may have heard that. This upper line here is the sort of standard curve for load on the system. It sort of starts off early in the morning. You have a peak in the midday, and then it comes down after the midday. As you start to add more and more solar into the system, including and also wind in some cases, but mostly solar, the grid doesn't see it as generation, it sees it as reduced load. So you're using your own electricity. It's like you're shutting off the lights in your house. So the grid, instead of seeing this load, is seeing this dip in the load, saying there is no load there. And then what happens when the sun goes away? Oh, excuse me. The grid has to ramp up during this short period of time when solar power is going down. But the use for that, especially in the summertime at 4, 5, 6 o'clock in the evening, we're coming home from work, turning on our air conditioner, that load is increasing. And how do you supply that? You may have heard in California with the heat wave that happened, they had problems with the grid. They had to ask people to lower their use of EVs during this period of time. That's called the duck curve. And their response to that was to ask to have natural gas plants built small natural gas plants to take care of this ramping capacity. We're now seeing batteries replace some of those natural gas plants. But again, that's the issue of transforming the grid. As we put more and more inverter-based systems, we have to figure out, how do I address this duck curve so that I'm not having to build more and more natural gas plants as I build more and more solar plants that I add to the system. And that gets into the issue of planning. We have to do integrated distribution planning. So we understand, as we electrify buildings and the transportation sector, we're going to double the amount of electricity. Not only are we going to double it, but we're going to increase the electricity in the wintertime because we're building out heat pumps and EVs. Heat pumps use more electricity in the winter. EVs are less, have more charging performance needs during the winter time. So how does that all change? We need to do what's called integrated distribution planning. Part of the 2019 Energy Master Plan required this of the utilities, but they haven't done so yet. So part of what you're asking for when you say, I want to electrify the transportation system, I want to electrify buildings, I also want the utilities to do integrated distribution planning. It's part of that, looking at that whole system as an integrated, holistic system instead of just a piece over here on solar and a piece over here on EVs. So that's my little short side trip on grid integration. So back to Solar 101. So you put the panels on your roof, you get them connected in parallel and series, depending on your current needs and voltage needs. So a little detailed. We showed this before, a string of solar panels on one side, a string on the other. They're all connected with these little connectors called MC4 connectors. They're standard. They go into that controller box that goes into the inverter. In some cases, you can go to now to batteries to store your electricity. And your inverter inverts it to be able to use in your house or to send it out to the grid. Just a little detail on that combiner box. It's basically a surge protection. It's basically a circuit breaker on your system. You can see here all of those wires from the strings of panels come into the combiner box and then go out to the inverter. So a little more detail to explain that. So here's your string of panels, and we'll talk about, the different types of panels that you can go buy. Get connected into the combiner box. There's still DC that goes into the inverter. The inverter changes that from DC power that's produced in the panels to AC power to be able to be used or to send out to the meter through the meter into the DC power grid. In some cases, it's, you have this second meter that's recording the amount of electricity that you actually produce. In some cases, you're sending that DC power into a battery that's storing your electricity on site. And that battery use then has to be, it's being charged at DC power, just like your car is DC power. And at some point has to be converted to AC to be able to be used in your home. Every time you convert that electricity from DC to AC or AC to DC, you're losing some of that power. And that's one of those equations that we showed in PV watts, is how much loss do you have in your system. Typically, overall, you're getting a 15% loss in the wire loss of the system, the conversion in the converter box, the conversion in the inverter. So every time you transform that electricity from AC to DC, you have some of those energy losses as heat. So we talked about that duck curve of the adding more and more solar on the system, because that solar power starts to generate when the sun starts to raise and is peaked out during the peak of the day and then starts to decline towards sunset. So you can see this parabola is the path of the sun from sunrise to the peak of the day. And you want to calculate, when you're building your system, how much energy is being is hitting the ground or hitting the roof during the entire time during the day, that goes into being able to calculate how much your system is going to produce. Remember in PV watts, we had that column that said, here's how much solar energy is going to hit your panels during the day. That's calculated by this area under the curve. To make it a little simple, you may see this expression called peak sun hours. So it's the number of hours during the day that the sun is providing 1,000 watts per meter squared to hit your panels during the day. So you can see the area under this curve is the same as the area under this rectangle. There's about 4.5 kilowatt hours that hit the ground per meter squared per day in New Jersey when you're calculating how much energy your solar system is going to produce. So you may hear this term called peak sun hours. It's just how much energy is going to hit your panels during the day. And then you also have to think about, that the system, that the solar energy changes over the year. So it peaks out during the summertime, and it's less during the wintertime. So in the summertime, you have 16 hours of daylight. In the winter, you have 9 hours of daylight. So over the year, you have to calculate on a monthly basis how much energy during the day is going to hit the panels so that I can calculate how much energy I'm going to use over the year. Net metering helps to net out those differences, but if you were off grid, you would have to calculate that. And as we start to shift to electrify buildings, we're going to shift this load curve. So this is a typical load curve of a household, sort of peaks in the summer when we're turning on our air conditioners, in that shoulder months in the spring. We don't need to turn on the lights. We're not turning on the air conditioner. We're not turning on the heat pump. I mean, we are turning on the heat pump, but in this example, before heat pumps, we're not turning on those systems. So the load curve looks like this, shallow in those shoulder months and a second peak in the winter, but a higher peak in the summer. As we shift to electrify buildings and start to use heat pumps, they're going to use more electricity in the wintertime. So you're going to see this curve have two humps. It's going to have a peak here in the winter and a peak in the summer and a shoulder month. And you can see the amount of electricity that's generated in the winter months is less than the electricity that's generated in the winter month. But we're also adding higher load in the winter months. So the load is going to be up here and our panels are generating electricity down here. And we have to start to think about, how do I build out those solar panels so they produce more electricity in the winter months and equivalent to the amount of electricity they produce during the summer months. So just a thought process. And we'll talk about how to think about that through the other slides in the presentation. So how do we get that number of that peak hours of energy that's striking the ground? So this is NREL's map of the solar radiation that's hitting the ground in energy, kilowatt hours per meter squared per day. And you can see New Jersey is about 4.5 kilowatt hours per meter squared per day, as opposed to here in southwestern California at about 5.5, 6 kilowatt hours per day. So you can see solar energy is hitting the ground across the United States, even in Alaska. You can put a solar system. The difference is I have to put a little bigger system in New Jersey than if I were located in this southwestern portion of the United States. It's just a matter of, again, to get the kilowatt hours produced that I'm going to use, I have to put a little bigger system because it's kilowatt hours per meter squared. If I want 10 kilowatt hours, I have to put a little bigger size of the system to generate 10 kilowatt hours as I would in the southern portion of California. But I can build the same system to generate that amount of power or energy.